Can you hear me?
Yep.
Yeah, okay. Hi. Let me share the presentation. 1 second. Okay. Can you see the presentation?
Yes.
Yeah. Okay. Thank you very much. Good afternoon again. Today I'd like to introduce you this work that we developed together with ex-collaborator Mike Milan Petkovic and Chigao, and has been recently published in Mechanical System and Signal Processing. This presentation is titled Interval Predictor Models for Epistemic Reliability Interval. So just to move straight into, so this is the paper you can refer to if you have if you're interested in the topic, but just to kind of clarify what the problem is and what we are trying to achieve. So let me first start with the problem statement. So what we are interested in is given a set of experimental observations, essentially n realization of certain explanatory variables x and dependent variable y, we would like to generate or prescribe a descriptive model with theta being some fitting coefficient and theta fitting coefficient that is somehow informative and give us an informative prediction on the output y from arbitrary values of x. So by informative, we imply that the model is capable of describing somehow the overall trend in the data, the spread of the error predictions, but also the probability or that a new observation will be contained into the predicted error range. So this we call model reliability. Now, if you're coming from my machine learning community, this sometimes is called generalization error. But so essentially, if we want to visualize the problem, just 1 second, this is essentially what we're trying to do. So this is, for instance, a data set of observation x and y of an unknown process. We don't have other information about the underlying data generating mechanism but the data. And what we could do, or what standard approach will be, for instance, to fit a least square regression model and then prescribe some confidence interval on the regression model. So those were computed using MATLAB, for instance, using standard approaches. And one thing that you can perhaps appreciate already is that actually more or less 1/3 of the observation of the samples fall outside from the predictive range. So we believe this is not optimal characterization of the error, of course. So what we would like to do is to prescribe an interval predicted model that better describes the error in the data, and for instance, give this kind of error trend in the unknown process. So one thing that I want to point out is that, as you might already see, the envelope kind of depends on some extreme observation that are on the boundaries. So in a way, if we were able to remove or discard some of the outliers, we could prescribe a much better interval predictor model, which better describes the uncertainty in the data. And in contrast with the standard least square confidence interval, in this case, the predictor model was rejecting only 5 of the samples in the data set and not 1/3. So again, the scope is of this paper is focusing on models that depend arbitrarily on the state x, and we will limit our scope on models that depends linearly on the fitting coefficient theta. Why this? Because we want sufficient richness to models complex dependencies between y and x, but we want a simple models in terms of optimization and characterization. So we want to be able to define this model very with the lowest computational effort, essentially. And again, we want to make informative prediction and rigorous uncertainty quantification. So we are interested in the overall trend in the data. We want to quantify and predict the error, also this model's reliability. So for quantifying the predictive error, we will use interval predictive models. Whilst for the reliability, which I will define in a second more formally, we will use a tool that comes from statistical learning theory that is called scenario optimization theory, scenario optimization approach. So the mathematical framework, a bit more formal, is as follows. So what we define an interval predictive model just as essentially a lower and an upper bounding function, f of L and f of U, that we define as linear combination of some fitting coefficients, U and L, which together defines our parameter vector theta, and basis function psi. So clearly we can select different basis functions, for instance, polynomial basis, radial basis, Fourier basis, and many others. But I'm not going to enter in the details of the selection approach for the basis function. This is a very problem-dependent task, and clearly a different basis function might lead to better results in certain cases. Another thing we are interested in, or that another metric we will take into consideration when we define those interval predictive models, is the prediction area. This defines somehow the tightness. I mean, we can call it accuracy if you want, maybe it's a bit misleading, but let's say the tightness of the prediction interval. And this is just defined as the integral of the difference between the upper bounding function and the lower bounding function over the domain of the explanatory variable x. So one thing to notice is by definition, because we have linear combination of basis and coefficients, we can actually compute this area analytically if we have an integral derivation for the basis function. Another indicator, as I mentioned before, is the reliability of this model, or similarly the error probability. So we define this as just the probability. So the reliability is going to be the probability that, given a new, not yet observed pair y and x, the dependent variable y is going to be contained within the interval prescribed by this model in correspondence of the x. And in the same way, the error probability is just going to be 1 minus the reliability. So you can see, for instance, here we can generate more samples, or we can measure more x and y's, and the blue markers are going to be the one that are going to fall outside from the bounds and define essentially the error probability of our model. So one issue that I want to point out is that, I mean, we can try to estimate the error probability and the reliability, but we need to get more data, and this can be expensive. And furthermore, the true value of the failure probability and the reliability are only known asymptotically. So we can approximate it if we want, but we require cost, effort, and we are not sure about the true value, in fact. But scenario theory and statistical learning theory will help us with that later on. So in our work, we reviewed several different types of calibration or identification methods to prescribe those interval predictive models. So there are different ways that one can do that. One way is, for instance, to run a full data enclosure optimization problem, which is essentially a convex linear optimization problem, where we are actually trying to minimize this area metric while constraining all the samples in our data set, then samples in our data set, to fall between the lower and the upper bound. So this function g is essentially defined n constraints that are randomized constraints, because actually this is an x, I'm sorry for I mean, no, sorry, this is a delta, which is essentially comprising essentially the realization of X and Y. So those are randomized constraints because depends on the randomized data in our data set. And this G function is defined as the maximum between GU and GL, which are essentially bounds on the constraints on the lower bound and the upper bound. So another way we can try to optimize or to identify our interval predictive models is by trying to remove some of the outliers. So first we have to understand what is an outlier in our data set, and to find an appropriate metric to decide this essentially. So what we do is to use the value of the constraint function G as a way to identify outliers. So the highest value of the G function will identify samples that are the closest to the bounds, the upper and lower bounds. So another thing we can do is to look at the distribution, empirical distribution of those G scores for the samples and discard upper tails. Of course, in this way we can obtain an IPM that has tighter bounds, but this might affect the reliability of the predictions in the end. So one way we can define this optimization program is as follows. So we have the same structure. We want to minimize the area function, and we have some randomized constraints, but actually we have a reduced set. So we have just n minus n0 samples that we consider in our data set, and these essentially are defined by this data set. This reduced data set is defined by this by the criterion I just explained before. So that we remove essentially samples from the tail of the G distribution. So in this way, we can find an IPM that somehow have tighter bounds, and we can accept somehow lower performance in terms of prediction, or better performance in terms of prediction by removing low probability events. One problem with optimization, let's say program defined before, is that we have that the constraint somehow changes. The important samples might change while we are optimizing the coefficients. So one thing we proposed is another optimization program. This is a soft constraint or a regularized interval predictive model design. So essentially what we're doing here is to add some relaxation terms, theta, which essentially slacken the lower bound and upper bound constraints. So one interesting thing about this formulation is that it's continuous, it's linear, and also we have this raw parameter that we call cost of violation parameter, which can be used to trade the tightness of the interval predictors for reliability. So this is an example of this interval predictor identification model used on a different data set. So one thing to notice is that for rho that goes to infinity, the soft constraint program goes back to the formulation, to the first formulation where all the sample constraints were all the samples were constrained to fall within the lower and the upper bound, and this is presented in the top figure. But we can lower the cost of violation, and then we start discarding essentially samples from the boundaries of this predictive model. So now, finally, one of the most, I think, to me, interesting part about this is really about trying to assess how well is our model going to perform for samples that are not yet observed, samples that are generated from the same unknown mechanism, but not yet observed. So how good is the model prediction? So the reliability is just as I explained this, and what we will use is scenario optimization theory to render distribution-free, rigorous, non-asymptotic bounds on the error probability. So they have some couple of reference here, like scenario optimization theory. I think the first paper was 2008 or a few years before, and is applicable to a wide range of optimization problems, not just the interval predictor models, but we will use this theory specifically for this case. So just to give you an example of some of the theorems that are prescribed by this theory, and some of the assumptions needed. So one of the classical assumptions that the optimization program has to be consistent, which somehow implies some permutation invariance of the theta star, the optimized result, once we shuffle the order of the constraints. And there is also some non-degeneracy assumption. And those essentially are quite good assumption, very good assumption for convex optimization programs. Another assumption is the data sequence is independent or stationary. So this might be a strong assumption in certain application, but those are the only, essentially this is the only assumption that is needed on the unknown data generating mechanism. And there is no need to, for instance, prescribe specific distribution or distribution family, or assume other assumptions are not made on BGM. So given those assumptions, some of the theorems can be that are offered by the theory are as follows. So I presented two. One is a data independent theorem they call a priori, and the other one is data independent or a posteriori. So the main difference is that the data independent or a priori bounds are obtained can be obtained even before solving the convex optimization program with randomized constraints. So the idea is that we can bound. So if you look at the lower left box, we can bound error probability to be lower than a certain epsilon value or reliability coefficient up to a confidence level 1 minus beta. And this reliability parameters, once we fix beta, only depends on the number of available samples in our data set and on and theta, which is the number of optimization parameters. So similarly, but differently, let's say the data-dependent bounds are computed a posteriori. So first we have to optimize, design, observe this optimized theta, and then we have a similar theorem, but the difference is that our epsilon parameter, the reliability parameter bounding the error probability, also depends on this quantity S and star, which is defined as the complexity of the optimized solution. So this complexity can be computed a posteriori once we observe the solution, and is essentially the number of samples we strictly need to recreate the optimum. So there is a very strong analogy with the branch of the statistical learning theory that is called compression learning. So you can also check that out if you're interested. But the point is that given the number of samples we have, the complexity of the decision, and the confidence level we select, we can then bound with high probability, with high confidence, the probability of error for our IPM. So again, I mean, if you check the reference I presented before, there's a summary of some of the most commonly used bounds that come from scenario theory and then are prescribed for different type of optimization programs. You can see those in the table below. But the key feature is that, again, are distribution-free, non-asymptotic. Well, a priori, a posteriori already described. But also we can, once we have this relationship between epsilon and the number of sample, number of optimization design parameters and the confidence level, we can also invert this theorem numerically, and we can, for instance, carry out some confidence analysis, or we can, given, for instance, the number of fitting coefficients we want and a certain target reliability level and confidence level, we can do design of experiments. So how many how many samples we need to reach those targets. Another thing we can do is model complexity selection. So let's say we have the number of samples, we have a target reliability level and a confidence we want to achieve, then we can define what's the maximum number of fitting coefficient, so the maximum complexity of the model we can afford to reach those goals. And finally, just a remark that from convex optimization programs, the complexity Sm star is always shaped by the number of fitting coefficients. So in a way, a posteriori bounds are generally tighter than a priori bounds, but as I mentioned, we have to first solve the optimization program and then calculate the complexity to essentially get those reliability certificates. So just to give you an example, again, going back to the previous case with the data set, one thing we can do is to tune our relaxation term and trade off area for failure probability. So in this example, we have 2000 samples on the x-axis. And if we have a very high cost of violation, then we're going to have the largest area value. But also in red, we will have the best performance in terms of probability of failure. There's going to be around 0.01 in this case. So the chance that another sample drawn from the same mechanism is going to fall outside the bound is contained within this epistemic, let's say, reliability interval. On the other hand, if we reduce raw, we have more violation like in the right-hand side, but then we inevitably decrease the reliability of the model up, for instance, the worst case to between 0.05 and 0.1, the failure probability. And well, another thing I wanted to mention is that there's this high correlation between the complexity. So this k over n is, this k is actually our S of n. So it's the complexity of the optimized solution, the number of samples we need to reproduce the optimum divided by the total number of samples we had in our data set. And there is a high correlation between this ratio, so complexity ratio, and the bounds of the failure probability. So to conclude, so these methodologies allow trading essentially tightness and performance of the IPM interval predictor model for its reliability. We can use it to calibrate essentially the response of the prediction error. And also we obtain a certificate of reliability that essentially is mathematically derived, doesn't require empirical estimation, and essentially comes for free, and quantifies somehow the lack of data and model over complexity. For future challenges, so far there are a few attempts I've seen already, but I didn't try yet of multi-input, multi-output cases. Also non-convex dependencies in theta of our model, we didn't explore yet. And also extrapolation beyond the domain of the served data might be a challenge, as well as non-stationary data generating mechanism. So this is all I had. Thank you very much. Please refer also to my, there's a repository, a MATLAB class for this. But I mean, I guess it will be at a certain point very interesting for me to kind of try to extend it or translate it to Julia. So there's just something I want to mention. Thank you very much. Please, if you have any questions, if there's time.
Thank you very much, Roberto, for this interesting talk. If there are questions, please go ahead.
Yeah, I have a couple of questions, but thank you very much, Roberto, for the talk. Can you go into the practicalities of, I mean, how to deal with the outliers? I mean, I have a given set, which is very costly to have obtained. I'm thinking about the time series. So I cannot provide a new element for that series unless it is for the future. How do I sort out the data to find out whether I have an outlier or not in an automatic way?
Okay. So I guess you're, for instance, in your case, you're talking about series. So
yeah.
So one assumption we are making here is that the samples are IID. So we consider the combination of X and Y as like just scatter. So we don't link them together in a way that there's a difference there, right?
Okay.
But if you were considering your time series as just a cloud of points, then yeah, in a way, and maybe you also have a model that describes your process already, or some kind of idea of what can be. Then what we did for our case was just to essentially try to plot the to compute the distribution of distances from the upper and lower bounds, and just start identifying the samples were the closest. And so this is the way we dealt with it. But outlier identification is our, I mean, I know there's a huge literature and different ways of dealing with it. So
yeah, and can you go back to the previous slide, because I have another question. And so around in the X direction, 0 to 1, there is some sort of clear trend, which is not captured by the blue line. Now that would suggest that either you increase, say, your basis set, or I mean, modify, say, your model description to catch up that oscillation. Is there an automatic way again of detecting those kind of things?
Yeah, automatic. I will have to think about it. I like, for sure, like one way would be to increase the number of bases. So the more bases and coefficient you add, the richness is gonna, the more rich is gonna be your regression capability in this case, for instance. But then automatic is that's a bit of a challenge. Like decide how many bases and what kind of bases you need is just it's more an art than a science, I feel, at least in this case. Maybe, but I mean, I also didn't work too much on that specific aspect, I guess. So if you have any idea,
no.
I mean, I'm more than welcome to discuss it, actually.
I have questions, not yet ideas, at least. And a final request, could you share the paper that you were mentioning that you just published?
Yes, absolutely, no problem.
Thank you very much. Huh? Nice talk.
Thank you.
Cool. Is there any other question for Roberto?
Seems no.
Okay, thank you again, and yeah, sure. Thank you very much. I think we can move on to the next
thank you
speaker then.